Okay, welcome to How Things Work. I'm Lou Bloomfield. I've been teaching this course approximately in its present form for, well, since before most of you were born, which is a little bit horrifying, but it's okay. I'm still waiting for someone to come up to me and say that their parents had me, so it hasn't happened yet. I've had simultaneously mother-daughter pairs, but that's all. You know, that's cheating. So I'm going to start off today, just give you a background on the course, try to remind us both of some of the just details, logistical details about it, and then start doing what I do, which is to talk about physics in the context of everyday objects. The first one being skating. So that's where we're headed, but I'll start off with odds and ends. The first is really, what is physics? As we'll discuss shortly, many of you have taken physics, but we'll come to that. But basically, it's the study of the way in which the physical world operates, how the rules governing its behavior. So it explains how our universe works. And before I go too far in this, I put my lecture slides online so that those of you who are trying to transcribe, hopefully we'll be able to save you that particular effort unless you find it useful. But okay, so physics is explaining how the universe works, and it's useful because not only does it explain how the universe works, but it allows you to predict how things will happen that you may not even have encountered before. It addresses a lot of how and why questions, and so you'll see that most of the questions that I come up with or ask in class or out of class are how and why questions. They're not the what, where, when, who. That's I don't know. That's other disciplines. Naming stuff is other disciplines. The physics is in how does a skater move, and like why do they keep going when they stop doing anything? They just what's coasting? We'll see that shortly. I view it, and I think others would agree, that it's a key component to science literacy. So part of my mission in doing this course is to give you some basic science literacy that should help you in your real world. Physics underlies more and more of our technological society. All these things that you encounter, the gadgets that you encounter, they're based on physics. And there are clearly some very important societal problems, human problems, that are physics that can be explained and understood in terms of physics. For example, climate change. It's not an issue of belief or policy or politics. It's real. It's happening now. You're living through it. You guys will live through it more than I will. And it can be explained in terms of physics. In fact, it's relatively straightforward to explain why putting lots of these so-called greenhouse gases like carbon dioxide into the air, why that should ultimately lead to an increase in the temperature of the Earth. So that's background in physics a little bit. And incidentally, let me start right off here, is I may be a bit of a showman, but I'm not a performer in the sense that I memorize my lines. I have had professors, probably you have too, who they're like perfectly organized. And 13 minutes into lecture 7, you knew where they're going to be a year in advance. I literally had professors like that. And it's perfect, okay, right? But I don't do that. In fact, I'm winging it all the time. Therefore, ask me questions. You can redirect the class with a interesting question, and there are no dumb questions. Do ask questions. I know more and more it's intimidating to raise your hand and disturb the peaceful nirvana that the other people in the class are in. Oh, you asked a question? Okay. Please ask the questions, okay? So here I'll go head right off doing what I'm doing, but you can, if I say something that doesn't make any sense or that elicits some interesting question to you, ask it. Okay, so having said what I think of physics, what about this course? It's a course that teaches physics in the context of objects. So we go object by object through the world. Strategically chosen objects, they're not just willy-nilly. I pick them and order them on purpose, but it's the objects that are the highest priority. And within those objects, we'll find physics concepts, which is to say, ideas and understanding of how things work. And finally, on occasion, we'll encounter formulas, mathematical descriptions of these concepts. People who do physics for a living, the formulas are really important to them. But for you all, the understanding comes in the concepts. That actually makes the class harder rather than easier. For some of you who've had physics classes in the past where you did a lot of calculations, the calculations, I've heard 100,000 million times the idea that I hate math, but on the other hand, I love the formulas because you can memorize the suckers. And then you can give me an F, give me an M, I can give you an A, and earn an A. There's no understanding of that. And I do it backwards then. So it's a backwards course in physics. We don't go formula by formula through the world. We go principle, object by object. I sometimes get lost in the details, so I get stuck more on the concepts than the objects. But if you all will help me, work with me, and remind me to come back to the objects. So that, for example, when we're talking about bicycles, I've had wonderful discussions in this class where people brought up the topic of motorcycles, which I have actually never ridden, not particularly eager to get on one. But the experiences of riding a bicycle, riding a motorcycle, are the same in some respects and different in others, and it's sort of interesting to work through these things. So if you remember the objects and objects that you've dealt with, bring them up, okay? My job is to tie everything together so that even if you bring up something that's different from my topic, your topic, we'll still get the same material out of it. It'll work. So this class is sort of case study physics. It's therefore not a new invention in concept. The grand concept of how to do the course, it's same old, but for physicists, it's relatively new to do case study physics. Again, it's the how and why questions, and really it's how physicists discovered physics. Scientists discovered physics. They didn't set out to find a principle. They set out to explain the real world. So a Newton principle got started watching apples fall and wonder whether gravity is the same on Earth as it is for the moon. And that train of thought led him to figure out a lot of really important things. Okay, some goals and expectations, my goals for this class, for example. I'd love to have you develop your understanding and intuition. You can look at the world around you, certain things make sense to you, certain things you had intuition about how they will proceed. You've never seen, for example, a car that was heading towards Richmond just instantaneously begin to head away from Richmond. You know that doesn't happen. So it's part of your intuition that if something's going one way, it's not going to instantly reverse its direction. So your intuition is good in some respects. It's also misleading in others, and so we'll encounter these various things that your intuition will mislead you, things you expect to be one way and they're not, often for interesting reasons. What else? Appreciate the role of physics and science in general in your life. It's for many of you, and turns out sort of my mission in life is something like what I'm doing now with you all, trying to help people who won't go on in physics. Physics is not, you're not going to major, minor, or anything in physics, but it's going to be useful to you somewhere down the road, even if it underlies your art or helps you design or make a building work better for you. You should see the universe as predictable to an extent. It's not. It is predictable. There are aspects of it that are not predictable for interesting reasons themselves. So, but it is, in some respects, a wonderful, magnificent machine. Not to, okay, I'm not talking about free will issues and all that, but it has aspects to it that really are wonderfully understandable. And hopefully you'll end up learning to find science interesting, enjoyable even, and not something you have to be afraid of. Physicists do have a bad habit of trying to blow away the audience. It happens among physicists. Physicists giving talks to other physicists sometimes feel better about themselves when they blow away the other physicists, which serves no purpose. The other physicists usually aren't so impressed as they are thinking, what a jerk, okay? So, I'm trying to give away all the secrets. It's the opposite of magic. But sometimes I talk about this as unmagic. I mean, physics taught as magic is this little gadget, which is called a love tester. Yeah, chuckle, chuckle, chuckle. And if you hold the bottom and the liquid goes up, and I know some of you in back can't see the liquid going up. The liquid's going up, evidently, I'm a good guy here, right? And go, ooh, that's science, wow, right? That's just showmanship, and it's a joke. There's no understanding in it. So, right, there is some aspect to that among physicists and science people teaching in general. That should be not what I do. That's magic. It's stupid magic. My goal is to give away all the secrets, which is the opposite of what magicians do, right? They try to keep the secrets, they try to deceive you. I'm trying to undeceive you. So if I do demonstrations, and you'll see there are lots of demonstrations in this course, it's probably the most fun when there are demonstrations. The demonstrations should always serve a purpose. They should illustrate some concept I have in mind. You should be able to follow them, and you should understand why, in the end, why they worked out the way they worked out. And if that's different from what you expected, great. Learn from it. If it's what you did expect, great. Your intuition and background is helping you. So any demonstration in which you come away going like, what the heck, then I failed. So help me try not to do that. What else here? I expect you to think. That is a challenge for many of you who are more interested. It's hard to turn on your sort of thinking cap and go, oh, what's going on here? But that is where the understanding lies. It's in really thinking about the stuff and internalizing it. It takes time, it takes repetition, but that's where I want you all to go. Formulas, there are a couple of them that I'll want you to know. They really live within the concept, so that if you understand the concept well, a formula comes naturally. It's not like some random other thing to bring along. What else? I assume no prior study of physics. So those of you who are worried, like, well, I never did take physics, am I really at a disadvantage? The answer is almost certainly no. Incidentally, there are some people in this class who took the other semester, the spring semester, in which same story, but different topics, and therefore different portions of physics. Those of you who took 1060 will get a couple weeks. I'd say 2 here. It's a little longer than 2. Of review, and my experience has never hurt anybody. If it bores you to tears and you see the same jokes and you anticipate my jokes and you want to leave, you can leave. It's okay. All right. So I used to use electronic clickers to have you all respond. It turned out it ended up being taking attendance by accident, maybe on purpose, but a mixed. And I dragged people here who didn't want to be here, and they would sit in the back with all their friends' clickers, clicking in and watching movies on their gadgets. And it's not what I wanted. So I've stopped using the electronic clickers. But I'd go back to the Victorian age way of responding to questions, which is like voting with your hands. Or if you're really sheepish, you can do this. Okay? So the question at hand is, what's your background in physics? So this is mostly for you all to see. I know what the answer is going to be, but A, B, C through E is a throwaway, right? If you went last time I did it was Berkeley. This time you're a Caltech 12-year-old. I got to change something. So how many of you have never taken physics? Okay. How many of you have taken some but never taken a physics class? That is like a So it's a little encouragement. How about you taking a year, up to a year of physics? See, this is almost everybody. Have taken 2 years of physics, okay, some, and then, okay. In the year of the clickers, we would get some votes for E. But then we get votes for E when there were only 4 questions, 4 answers, right? So, yes, a few people, yeah. All right. Related question, sort of, is I'm giving you 6 physical quantities, which I'll talk about physical quantities soon enough. Can you distinguish these pairs? Velocity from acceleration, and mass from weight, and force from momentum. You okay with the words in the question? How many find this baffling? You know, now you're into like the sheepish land, right? How many say you've got some sense of the distinctions? Okay. How about the C? I might be able to distinguish each pair. How about I probably can distinguish each pair? Okay. And finally, I can definitely distinguish each pair. Okay. So it's peaking between C and D. Probably there are very few people who are really absolutely sure they can do it, which is fine. I mean, that's par for this course. All right. So some things to do. I'm almost done with my little introduction to the class. First off, please read the syllabus. It's online. It's not on Colab. I just gave up on Colab at some point. That's the address for it. It is also indicated. Is it indicated on this sheet? I left off the most obvious link. Oh, good. Yeah. Oh, it's up here in the little in the image up there. But that's an abbreviated version of the syllabus. Incidentally, those of you who don't have it, it's fine. It's up here. Come and get it when you're done. But it just gives you an idea of the background of the material on the class, the approximate schedule of classes themselves, and some odds and ends about how the class is the work I assign, which is 9 problem sets, 3 exams, that is 2 midterms and a final, and some work online. And that brings me to say 2 cents about the online book. The only requirement for this class is that you have that online book/learning environment. It's described on here. A physical print book you can get it or not. The online version of the book is becoming better in the way it should have become better. It should become better. It's the 6th edition. Okay, I wrote the book. It'll have things, you know, you'll read things you've heard before to some extent because I write the way I talk. But what I've done recently with the most recent edition, the 6th edition, is I turned many of the figures into videos because a still image of something that's physical is often underwhelming. It doesn't show you. Physics is all about things happening, evolving with time. And a static image doesn't do that. So I've turned a lot of these things into animations with or without me involved. And hopefully they're more instructive and engaging. So watch the video figures. If you've got things to tell me about them, please do. Okay. What else here? Watch the online videos. That is, I videoed this class. We're being videoed right now. Hi, that camera up there. Okay, and I'll put it online after class. And so some of you who feel like you can watch it on your time rather than our time can watch the online video. Pay attention to your own power, character and willpower and stuff. A lot of people will tell themselves, oh, I will watch it online. No, I can skip class today because I'll watch it online. Yeah, some people do, some people don't. So, okay. There's an online practice system associated with the ebook, this Wiley Plus learning space environment. That will be a small part of your grade, is actually doing those practice assignments. And hopefully you'll find them in, again, a good learning experience. If you've got issues with them, tell me too. It's new to me as it is to you. This is something that I haven't done before. It wasn't available before. I wrote many of the questions in their original form. They've evolved over time and have gotten out of my hands, and some of the questions weren't written by me, and I may look at some of them and go like, that was ambiguous. In any case, those online questions are scored, it's more like 60%. Getting 60% on the right is perfect. It's good enough. You get a full credit. So it's just do it. Just work your way through those questions. There's also an online chit-chat environment. Go ahead and get started with that. I'll try to pipe up in there from time to time. I prefer to communicate and interact with you all face-to-face. During class, before class, after class, at my office hours, I have no problem with technology itself. I've been immersed in it for a really long time. I'm one of the rare digital natives of my own generation, having grown up on a university campus with computers everywhere as a kid. So it's not that I don't like technology, but it gets in our way in a variety of forms. Which brings me to these final thoughts, the last of which is, I know many of you have computers out and open. I ask you to continue in this course. I mean, today I don't care, but from now on, no gadgets of any sort. I used to call this with my son, Victorian boy. I cannot compete with those electronic gadgets. You all are, many of you, are so addicted to them that you just can't leave them alone. You may think you're taking notes. Some of you can take notes, but I filmed, maybe it was about a year plus ago, I put a little GoPro camera in one of those windows back there, filming you all from the rear. And it was very interesting. It was a bloodbath from about the middle of the room, and before that, on back, of just the screens were filled with everything but physics. Minds were elsewhere. My favorite was a guy who was not only was he watching a movie back there, but he wasn't watching his own movie because he was on his phone watching another thing. So he was 3 deep in not my class. So we got to leave the gadgets alone. Just close them. Okay? I hope you understand. Somewhere in some class on how to teach at the university, apparently, someone described this, some expert described what I have just done as not student-friendly. So there. I'm not student-friendly. Okay? Sorry. Okay. There, now I've completely lost my audience forever. You'll never talk to me again. So finally, my last thought, ask questions and volunteer in class. When I'm on my game and focus properly, I'll have you do the demonstrations if it's reasonable, not me. It's more interesting for you all to see yourselves do it. I've done them, I know how they work, and it's boring. You can do the demonstrations yourself after class. Here again with technology, I have observed over the years that people are itching to get out the door so they can get back to the gadget, right? Jonesing for the next messages, right? If you can put that off for a few minutes, come on up and do the demonstrations. Some of them, okay, they're just fun, and some of them you will learn something from doing it that I cannot show you. There are a few demonstrations you'll see down the, I'm thinking of them in particular ones, further down the pipe that you cannot imagine what it's like, a bicycle wheel, spinning bicycle wheel, turning it around. You can't, in your mind's eye, feel the forces acting and torques acting on you until you do it yourself, okay? So please come up and muck around with these things yourself. Talk to me, this classroom, incidentally, is open before, the hour before and the hour after this class. So you can hang around, okay? Or come in and talk to me. During class, if you need to come in or go out, the back is probably the best approach. That takes you out to the 3rd floor, same stairwell, but the 3rd floor. Finally, I don't really mind if you just pop out of the front here and head off. That's okay. Same as coming in. There was one very, very memorable demonstration I was in the middle of with 2 people seated at 1 seat apart, right in the front row, when a woman came in and decided to sit between them. And they had to move their backpacks while we were doing the demonstration. Okay, that one was a little, that I noticed, okay? What else? Okay, and the electronic devices things. Any questions at this point? The things I have left out that are important or interesting? Okay, yeah. Which brings us then, first topic. So, this is the way this class is intended to proceed, is to go object by object, story by story, through the real world and find physics in it. And the first object is technically skating, but skating can include skateboarding, razor scooter, okay? It's the story of all the sports that involve a lot of coasting. And we'll pin down what coasting is very shortly. So I'm going to start off, first thing with skating, has been my style for a while, is to ask a question that ideally is challenging or difficult to answer when we first encounter it, but that'll get clearer shortly. And so the question for today, the introductory question for today is about rotary lawnmowers. And you all have seen, if you haven't operated yourself, a rotary lawnmower, nearly all modern lawnmowers have a container in which there is a blade spinning around. It's a shield so you don't get involved with that blade. But it's spinning around, and it goes along the grass, and it mows the lawn, cuts off the grasses. And the question is, that blade is spinning, it's very sharp, and it cuts off the top of the grasses. Would the blade still be able to cut those grasses if they weren't anchored, rooted in the ground? Right? Normally you're cutting grass it's a plant, it's got roots, right? So it doesn't just come up as you scoot by. What if it weren't anchored in the ground? What if the grass were just sitting there, still upright, but just sitting on somehow without tipping over, sitting on the ground, and the blade came along, could it still cut the grass? Any questions about the question? You okay with the question? How many think, yes, it could still cut the grass? How many think, no, it couldn't cut the grass? Okay, it's nearly unanimous, no, couldn't cut the grass. That is, the anchor is necessary. Okay, so that's the first time I'll ask that question. We'll come back to it. All right, some observations about skating. And here are now, okay, for many reasons I'm not on skates, okay? But razor scooter is pretty close. So the observations, just from mucking around with these things yourself, is that when you're at rest on a level surface, I have to balance here for a second, I tend to stay at rest. Right? This should already start the language should be familiar. That an object at rest tends to stay at rest. So when you're a skater or a skateboarder or a razor scooterer, if you're at rest, you tend to stay at rest. We'll pin down what tend means eventually. If something, however, pushes you while you're in that situation, so somebody comes up behind me and I can't push myself for interesting reasons, but if something else pushes me, like the table, whoo, off I start going. My motion begins to change. You start moving in the push's direction. There's actually a fair amount of insight in that. The push and the direction you end up traveling, they're very closely related. In fact, they're the same. So a push to the right is different from a push to the left. All right? This is just familiar, I hope. Any thoughts or questions? All right. If, however, you are moving at some moment, so and nothing bothers you, so don't look yet. The story hasn't started. Let me get started. Okay, now I'm moving. I tend to keep moving. In fact, I tend to keep moving in the same direction. Here now is one of these cases, like I mentioned 20 minutes ago. You've never seen something that was moving to the right, just instantaneously start moving to left. Things tend to keep doing what they were doing when they're moving. If something does push on you while you, the skater, are moving, say, to the right, it affects your motion. You either speed up or slow down or turn. All right? So these are all, hopefully, fairly familiar observations about the real world. Oops. So, again, as is my style, and you'll see these, the way I work my way through, we work our way through a given object is through a series of questions, most of which are how and why questions. So these are all, there are 3 whys and 2 hows. So the first one is, why does a motionless skater, you'll see these again, and don't feel compelled to write them all down. You can get them online after class too. They're associated with the schedule. That schedule is printed here, and on the website, it's live, and it's got links. So the word skating is a link to these slides. All right, and I try to, they evolve from year to year, so they're all live now, but after skating, they link to last year's slides. Some hour, 2, 3, 4 before class, they will update to this year's slides as I second guess myself and change things. So first question then is, why does a motionless skater tend to remain motionless? And here it is. And it's an observation about our universe, and it is simple. It says that a body at rest tends to remain at rest. It's an observation that this actually was not a trivial observation. People had to, the great philosophers / scientists of ancient times or hundreds of years ago had to think long and hard about some of these things to be sure they got them right. And so this first one is, you've all heard inertia, that object at rest tends to remain at rest and object in motion tends to remain in motion. These were not trivial observations. It took a long time to figure them out and get them right. So this observed behavior that an object at rest tends to remain at rest is known as inertia. And I can illustrate for you inertia. So the first demonstration in this class, other than tootling around the razor scooter, has been for ages and ages, this one. Place setting on a silk tablecloth on a table. And it's not right without wine, although I, for many years, have used disappearing ink as the red wine because occasionally I end up wearing it. It's a pretty simple demonstration. You're welcome to try it after class. In fact, please do. You might set aside the wine part of it. But here's the idea. It is the case that objects that are left to themselves tend to keep doing what they were doing in terms of motion. In this case, these are objects at rest, and it is their nature. It's the nature of our universe that things that are at rest tend to remain at rest unless you bug them. We'll talk about what bugging is shortly. It involves pushing and pulling. And the fancy name for pushing and pulling is called force. So if you don't exert a force on them, they will tend to keep doing what they're doing, namely in this case, being at rest. The issues underlying this are that when I pull that tablecloth, it will exert a force on them, a little one. You know, you're used to it. It's called friction. And it will bother those guys, and it will make them start moving a little bit. I can minimize that effect by going quickly. That's the reason why you go fast. By moving fast, yeah, the friction's there, but it acts for such a short period of time, it just doesn't have time to make much difference. So I got to go fast. I also have to not pull up, the usual issues. So I choke up. I come out here, and then I go in close. So what I'm going to do is I'm going to snap this tablecloth as fast as I can, pretty much. And the objects should stay put, not because I'm holding them there or something, but because I'm not exerting much force on them. Okay? They're pretty much left to do what they were doing. Ready, get set, go. Thanks. I have learned over the years that I can never get complacent about that demonstration. Because you go, oh, yeah, that's going to work for sure, and I end up with the stuff all over me. So please try it. So try it after class. This is unbreakable, right? Not so. Put this aside. Try those guys. No problem. As instruction, you do want to choke up. Hold the cloth out here. Get close. So there's a limp part here because you want time to get up to speed, and before it snaps fast, snaps taut, and starts moving. All right, any questions about this? Thoughts about it? Okay. There's another version of this. Actually, do I want to do it yet, or do I want to? 1 second here. I'll keep going, then I'll come back to some more demonstrations. The time will work out okay. The second observation is that in response to the question, why does a moving skater tend to continue moving? And this is the other half of inertia. Another observation about our world is that if you leave something alone that is moving, it tends to keep moving exactly as it was before. We'll have to pin down what it means to say it's moving exactly as it was before, but it is interesting observation. So these are the two halves of the concept of inertia. Inertia is not a specific law. It's not so mathematical in its underpinnings, but it's an observation about our world that based on incredible number of observations, is known to be correct. It's and predictive. It tells us how things will behave. So that's the second half of inertia. And putting those together, we now get actually what is considered to be a law. It's called Newton's first law of motion. It's in a primitive form because I've got some language issues to develop. And the observation, the so-called Newton's first law, is that an object that's free of external influences, it basically is not being bothered, moves in a straight line and covers equal distances in equal times. So it goes straight, and it's ticking off the same distance every unit of time. That's an observation about our world, and now it's getting specific and quantitatively meaningful. Physicists refer often to an object that is motionless as moving with no speed. So this may be disturbing to some of you when I talk about motion and don't single out motionlessness as special. It's not so special. It's just the case when the speed is 0. You're not going anywhere. So that's just as a partly a reminder to me, because for some of you, things I take for granted, you don't take for granted, and therefore I can gloss over them or leave them behind, and you're going, what did he just do? That's impossible. It wasn't moving. So here again is a reminder, ask me. If you get confused on one of those, it's often because I left something out. All right, so I'm going to come to this question in a second, but first I got some demonstrations to do. First one, we'll go back to the tablecloth trick. As I hope you can see, it's not really a trick. It's our world, how our world works. Those dishes were motionless. I didn't bug them much. They stay motionless. They stayed put. There is a famous video online of somebody pulling a tablecloth out from underneath this elaborate banquet table using a motorcycle, and it's a fake. Physics is all wrong. Looks great, but it's a fake. It's physically impossible. They're doing it wrong. And why do I bring this up? It's because you live in not only in the real world, but also in this virtual reality-ish world. That technically that's not virtual reality, but you get the point. And these are the virtual stuff can be full of nonsense. It's not physics. It's not our world. So there's some confusion being thrown at you by media. Please recognize it as nonsense when you can. Dishes staying put because you're not bothering them. How about an apple? Okay, so this apple is going to stay put here, and I am going to come up and sneak a knife through it. Okay, the old demonstration a few years ago looked about like this. And the people in the first row, okay? So I changed, okay? This guy will come out in a minute. My spring-loaded knife. Ha! Okay? So there's an apple minding its own business all by itself. An object at rest, remaining at rest, and okay? Half an apple. It's a fun class to teach. You can't do this in an English class very often, right? Well, you can dress up as the bard, but it's just not the same. So that apple was sitting on the table. I could have greased the table. It wasn't a friction issue at all. Why didn't the apple get out of the way of the blade? What kept the apple in place? You tell me. Inertia. I'm hearing it. It's inertia. That's its nature. It stayed in place because that is its nature. Leave it alone, it stays put. The blade pushed on it a little, which is why it didn't stay there as a stack. Ideally, it would, if I got this perfectly aimed and really fast, the apple would just wouldn't move, and you'd suddenly discover it's divided in half. And that's my dream, but I can't pull it off. Okay, but you understand the idea? I hope. Next version of this. Those are objects at rest, staying at rest. How about objects in motion, remaining in motion? Well, if I take a banana, actually, and I get it moving, So that's before the story starts. So it becomes now an object that's moving to your right. It will tend to continue moving to the right at a steady pace, ticking off equal distances in equal times. That's the observation of inertia. And it's finally, as it included in Newton's first law, primitive form or otherwise. In fact, I can't get the banana completely left to itself because of gravity. Gravity in this case is a nuisance, just as friction was a nuisance up here. Gravity is present. It will influence the motion of an object so that the object will not go according to inertia perfectly. It'll go pretty close, but gravity will tend to make it bend its path downward. I can often get rid of the nuisance effects like friction or gravity by going to some extreme. For example, going very fast up here. Friction was present, but I went so fast, friction didn't have time to do much. And so I swamped it. I made it a bit player in my story. I can do the same with a banana. If I go slow, the banana, of course, is going to bend like crazy in its path. But if I go fast, okay, the banana went pretty well straight and true at a steady pace, moving along, right? Did they do the hypnotist this year? Is that hypnotist happened? No. The protector of fruit, for those of you who remember that, he knows to do the protector of fruit. I'm not the protector of fruit. Okay, it's an in-joke that'll be given away shortly. Okay, so I am now going to let the fruit go. I used to do a lot of egg work too, but we'll see about eggs. Anyhow, I'm going to get the banana going, and then I'm going to get my hand uninvolved. I obviously do not want to have my hand still going along with the banana. But I'm going to throw the banana, and it's going to encounter the blade, and it's going to continue on to the right because of inertia, right? Not because of me. So I didn't do it. The banana committed suicide because of inertia. You okay with this idea? Yeah. Before you all step on it. And, you know, these classic, we'll have it on video that you slipped on the banana peel. And I will spend the rest of my life in court. One more version of this, and then I'm going to come back to that question that I asked you at the beginning of skating. Last year I did spaghetti. This is linguine. I'm trying to get wider pieces, okay? I'll come over here like this. All right. Okay. I'll do it here. Always awkward. I can do it over there, and I'll have anxious people nearby. So here is the grass. I didn't say that. Here's the linguine, just here on the table, and the blade is going to come along, right? The floor now is littered with short pieces of linguine. For those of you who can't see it, they are not full length anymore. All right? The linguine had no roots. Which brings us to this question. A perfectly good way to end the hour. Remember this question? Rotary lawnmower comes along with its fast spinning blade, and the grass, instead of being rooted in the ground, is just sitting there on the ground, sticking up. Spinach, linguine, grass. Can the blade still cut the grass? How many think yes? How many think no? Woo! Yeah! That's correct. The blade of a rotary lawnmower cuts the grass mostly because of inertia. The grass just stays put. The blade sneaks through. That's why the blade's got to go so fast. If it goes too slow, the grass will have time to begin moving and will bend over. But the blade goes very fast. It has to be sharp, and this is why you don't want a dull blade on a rotary lawnmower. And there are lawnmowers that not only cut the grass once, but they will keep the grass elevated by way of wind effects, and they will slice it again. Those are called mulching mowers, and they cut the grass into little tiny pieces that in principle drift down and restore the soil and stuff. But anyway, rotary lawnmowers use inertia to do their cutting work. So what we'll do next time is we'll come back to Newton's first law, which I've been building on. We'll flesh it out with the proper language, which means introducing a few more words, a bunch of physical quantities, and that's where we'll start on Friday.